Good morning, everyone. And my name is Alex Matrosov, and I'm glad to be today here to present my keynote, Hardware Security is Hard, How Hardware Boundaries Define Platform Security. And actually, today we have these difficult times. A lot of conferences get canceled. I'm glad Hack in the Box in Singapore actually have online event, and all of us get opportunity to enjoy this awesome conference. So also this COVID-19 situation create a lot of interesting circumstances for security, and we will cover some of the topics today too. Few words about me. Actually, I'm leading offensive security research at NVIDIA, and previously I've been a security researcher at the companies like Silence, Intel Corporation, and ESET. So I'm doing security research since 1997, focused on reverse engineering, hardware security, embedded firmware devices, exploitation, and a lot of other interesting stuff, including automotive. Think about we actually have really a lot of changes in modern attack surfaces, and security industry visibility point actually just really like visible part of the iceberg. But we have a lot of modern persistence techniques which is tied to the hardware and firmware, and it's keep invisible for any endpoint solutions, and actually we don't have any automated tools and approaches for finding hardware and firmware implants. And actually it's creating a lot of differences in our modern attack surfaces and threat modeling approaches. I've been talking about advanced threat evolution last year and about researchers' arm race, where actually I've been focused at how the persistent threats get evolved and how the firmware currently playing the key for the differences of the persistent threats in nowadays. You can find this presentation by the link on this slide. But let's back to our main topic of the keynote, how security boundaries actually define the platform security. And think about hardware threat model really separated from the firmware threat model, but each chip on the device has their own firmware. And the problem is we really not define the threat modeling across the different devices on the board together. We're really separating it for each chip, individual chip, which is basically a mistake, because nowadays it's hard to spot real boundaries between different hardware and firmwares because it's communicating. And actually, if you get attack one chip, you can cross security boundaries, which will be making much more easier attacking other chips after that. It's why we should define the hardware threat model and firmware threat model together and not separating it. And actually, we need to look on the whole platform to define the right threat modeling. But actually, it is hard because we do have a lot of third-party components which is vendor not have access to, and it's just trust their OEMs, which is ship these chips and actually provide the firmware binaries to the platform developer. And it's created a lot of interesting spots in the threat modeling process. But let's back how usually security architects define threat modeling. And actually, look on it. this brilliant piece of the slide being captured from the UEFI forum presentation, and actually it says the analyzing security requirements and platform diagrams, it is enough to basically understand the threats and define the threat model. But in my opinion, really, if we just look on the diagrams and security requirements, it says nothing about threats. It just says a lot about what kind of firmwares and hardware components will be using on this device, but not really about the threat modeling, because you look on the requirements, you don't understand what kind of the firmware version, what really the chip does, what is version of the Bluetooth stack, or what kind of USB microcontroller will be using there. Even sometimes on the requirements, it's not defined particular OEM, and it's create a lot of blind spots on the threat modeling process. And it's hard to find real security problems in the platform diagrams, right? So based only on requirements. And if you look on the National Vulnerability Database, it is really numbers of vulnerabilities related to the firmware significantly increasing every year. So basically, we have already almost the same number of vulnerabilities reported by researchers and third parties to the certs from the vendors or US cert, which has been reported last year. So it's almost doubled already by the numbers being known from the last year. So basically, what's happening, a lot of vendors, it's the same actually presentation from UEFI forum, and a lot of vendors actually looking on the firmware through obscurity prism. What that means, if the security through obscurity works, the firmware binaries is actually available for everybody. Let's keep it private, and researchers will be gone. Nobody will be found the vulnerabilities. And this model actually doesn't work at all, because researchers can extract the firmware from the device, researchers can find leaked firmware versions in the internet, and a lot of other ways how it can be firmware get to the researcher hands. And if it's only the way for create the boundary, it is actually very bad practice. And I'm glad not a lot of vendors follow that way. And I really believe we should have access not the binaries, but technology specs also should be transparent to create the good transparency level for the other vendors who creating the hardware. Because think about modern clouds have this foundation based on the hardware, and if it will be no information about the hardware design, how we can trust this hardware? It's really hard. I was talking a bit about the persistent threats in my book, but today it's not about that. So I really like this picture, which is basically shows the cracking try to attack this guy in the bot. And I would say it is kind of like a joke about security architect, because security architects not really understand what the persistent threats and hardware or firmware plans means, and usually they do a lot of mistakes on the threat modeling about this kind of threats. As example, hardware and firmware security, it's not the same as a summary of all the boundaries across the board. As I mentioned before, we really try to separate security boundaries for each device on the system board, which is a huge mistake, because we actually really make a threat model focused on TPM, PMU or base management controller or embedded controller or GPU. And it is really separating different devices. But think about if one of these devices can be malicious, it's crossing the boundaries, and it will be equal boundaries for other devices in many cases, which will be basically create a lot of more opportunities for the attacker. What does that mean about the hardware security boundaries? Most of these chips are not under direct control from the hardware vendors. And it is really like third-party contracts, and vendor doesn't control the hardware and firmware, and even more, how you can create the threat model if this chip, it's not yours, right? So the threat model also need to be include the time of patching the vulnerabilities on the third-party chips and the firmwares, right? And it makes this process very complicated. Also, it is a lot of things connected to UEFI firmware BIOS, right? And also consider it to generate the trusted input-output interfaces, but mostly of the supervision scope of the main CPU, right? How we can trust anything that is under, not under our control. In current realities, hardware and firmware threat modeling shouldn't be undivided. Because we have a lot of ways how we, as example, can develop secure boot, right? And in many cases, secure boot will be, root of trust for secure boot will be TPM. In current trend model, hardware consider it trusted in many cases. As example, we just think our TPM is not compromised, right? And was brilliant research from Jeremy Boone about TPM interposer, and Tremel Hudson actually did pretty, not the same, different way, but also interposing TPM signals over soldering on the chip direct wires. And you can see this on the picture. And a lot of server boards actually have the separate TPM, which is just connected on the slot, and you can see it on the left side of the slide, which is also hard to consider trusted root of trust, right? But let's back to base management controller. So we just seen this picture where a lot of different components on the system devices exist, right? And base management controller, it is inside the trusted boundaries, actually. And what that means, base management controller, it is kind of like a remote interface for the system management board, because think about across the data centers, it is thousands of the devices, right? You can't go and physically reboot each machine or update each machine. So what that means, base management controller can update the system firmware, it can remotely reboot the machine, or even more, it can actually provide some debugging interfaces. And UEFI firmware actually blindly trusts most of the hardware because it is not under control, and how you actually can check it is a real device which has been originally installed by the vendor of this system platform and not faked by malicious attacker. But the hardware can attack UEFI firmware, and actually, in many cases, even more firmwares across the board. So it was very good research by Alexandre Gazette and Geoffrey Cherney on Zero Nights 2018. I really recommend you, if you're not seen yet, to look on it about their very interesting attack on Hewlett-Packard ILO BMC. But how many third-party chips in your platform? And actually, it is a lot, because we have a TPM, USB controllers, embedded controllers, fingerprint devices, touchpads, and many, many others. And all these devices has the firmwares. That means the firmwares can be updatable or not updatable. As example, your touchpad, in many cases, not authenticate the firmware. So basically, of course, it's not a lot of things you could do from the touchpad, but think about if it will be something more powerful. And we will be getting some places where common mistakes can provide really interesting opportunities for the attacker. Let's back on BMC. So BMC actually can update the firmwares for most of the devices across the board. So basically, even more, it can update the TPM and have an infinite control under SPI flash controller. It is have a separate network interface, not dependent on the system board interface provided for operating system and others. It's just separated for functional purposes. Also, in many cases, BMC has a DMA access, which can actually create additional ways for the attacker. And it's exactly been covered by Alexander Gazette and Geoffrey Charney on the research from the previous slide. But if you think about what will be if BMC can provide a remote interface for the debugging of the system board. And it is actually can be, because I just recently found on the American Megatrends documentation, they do have actually American Megatrends hardware debugger implemented in the BMC firmware interface and actually communicates over the network to perform host debugging operation. And actually, if you control BMC in this case, you can get even more privileges to attack very sensitive information and actually screwed up most of the security technologies across the board. And if you think debugging on Intel platforms, it's very expensive. Yes, it's been before Positive Technologies researchers not release their research about how you can create your own debug cable for $20, and it is actually make much more cheaper, because original Intel device being sold under NDA and being cost about $2,000, but it was not really a price for that, right? Also, interesting thing, when we have a deal with counterfeit devices with the hardware implants. And it is actually not rare situation where we can see this kind of devices used show up in the market, right? So, and it was recently F-Secure found Cisco devices, which has additional GTAC pins on the board, and it was possible to basically get full access over these pins to the Cisco router without having original credentials. Also, of course, you remember Supermicro case, right? And it is actually very interesting. We get much more attention after this Bloomberg presentation to the hardware implants. And I would say Bloomberg make very interesting thing to wake up the world to pay attention more on this kind of threats. But let's think about what happens in the cloud. We have this cloud ecosystems, which is powered by software infrastructure, and data center hardware provides the foundation for that, right? But we have the root of trust, which is inside the silicon. And what if something will be get wrong, right? So how usually we have root of trust separated from original system board? So in many cases, it gets implemented on FPGA, which is actually third-party chip, and or others third-party chips, which is basically provide some generic APIs and their own root of trust, which is not under control of the vendor. So basically, it's not changed much because we still have the third-party chip on the board, which is provide root of trust. But in this case, actually, Microsoft create Project Cerberus, which is being created for create this kind of a transparency for supply chain and actually attestation for the platform. Same thing, actually, Google been creating with Project Titan. At NVIDIA, we have a Falcon chip, which is also hardware root of trust for NVIDIA products. So it is actually very important for the modern cloud providers to have their own transparency and visibility across the device. Because if you have a third-party software and hardware control root of trust, it's really hard to validate it and understand it was not modified with any additional functionality or malicious code. I remember the case from previous year presentation when Alex Gazette and myself, we actually get down to Lenovo ThinkPad embedded controller just to understand how actually BIOS guard, was working. BIOS guard, it is Intel technology which is being created for armoring BIOS updates. But let's actually talk a bit about vulnerability in embedded controller. So basically, on this particular case, embedded controller was kind of a part of root of trust for security technology created by Intel. So how the update process for embedded controller works? We have an update tool which is based on generic Lenovo TDK update tool. Embedded controller update image actually mapped to the memory, and we set particular Lenovo EC firmware update in VRAM. After that, actually, after NVRAM variable is set, firmware start update process on their side. Basically, firmware loads the firmware image on the firmware memory and start validate the firmware header, and after that update EC firmware. If you look on this code, it is obvious race condition, time to use, time to check attack, right? So basically, if you look on T540p case, even more, it is just update embedded controller with unsigned binary. What that means? Even if the binary been signed by Lenovo, this model doesn't check any signatures. So you can modify any embedded controller binary and just flash it. But actually, embedded controller, it's quite powerful in many cases device. It powered in actually with ARC or ARM chips, and it can, in some cases, have a DMA access tool, and actually connected to LPC bus, which is also can be some way for the attacker to screw up the hardware. Think about, we have a lot of vendors involved on the firmware development nowadays. I'm talking about UEFI system firmware, and if you think about reference implementations, as example, can created by Intel, AMD, and then we have independent BIOS vendors like a Phoenix, Insight, or American Megatrends. Also, device manufacturers get involved because they basically develop the system boards, and original equipment manufacturers like Dell, Lenovo, Hewlett-Packard, and Apple have some additional code created just for their devices. And if you think about Dell, Lenovo, and HP, actually modifications came after device manufacturers. It is really small. It is kind of like about 10–15% of the whole code base. And it's not making huge differences because most of the code being provided by American Megatrends at Intel with a reference code for the technologies across the system board and new CPU features. If you think about how hard it is reverse engineer more than UEFI firmware, because it's huge complexity between different models, it is actually hard. So recently, myself and some colleagues released UEFI Explorer plugin, which is make UEFI firmware reverse engineering more enjoyable. So basically, we try to provide some automation for protocol reconstruction and runtime and system services initialization. So, but let's back to the attack surface and security boundaries. So you have a user application, kernel, hypervisors, it's higher stack. So if you think about the complexity of the attack surface and increasing privileges level, it is actually opposite. Because I would say modern firmware and hardware have much less complexity of the attack surface than modern software, but the privilege is actually very powerful on that levels. And Rob Woods from NCC was presenting on the last year Platform Security Summit this concept, which is I really like it. Also, last year, we've been seeing defeating Cisco Root of Trust security anchor, which is basically FPGA board. And it's been provide a lot of, basically, it's been provide additional layer of validation for spy flash, right? But if you think about the attack presented by Red Balloon researchers, what they did, they basically found the way how they can unlock the device for malicious bitstream. So in this case, if this FPGA trusted anchor get attacked, after that, all the upper layers of the boot process will be basically already modified by malicious attacker who have control under FPGA root of trust. Very interesting research, but it was additional research presented this year about Intel Max 10 FPGA, where Sergei Skorobogatov from Cambridge presented the way how he can unlock GTAC on this board. And unlocking GTAC actually provide a lot of powerful opportunities for the attacker to bypass security validation for the bitstream, and many others. If you think about FPGAs, it's actually any FPGA chip also has tiny microcontroller on it. This bootloader inside the silicon and unpatchable. The vulnerability which was found on Max 10 FPGA, it's been actually divided between this silicon-based level bootloader and some other stuff, and that means it is a silicon issue which is hard to patch in the field. So how we can reduce the silicon level risks and attacks? The Google did Open Titan project, which is actually open a lot of information and specification in the code regarding the Titan chip silicon. So Open Titan actually have much more visibility because you can check much more layers, not only the firmware, regarding how RTL is implemented on this chip, right? But also, anyway, we have some IPs from third parties, which is still is blind spot. And chip fabrication and production, it is also based on the third-party fabs, right? But anyway, it's created huge differences between traditional root of trust chips. And it's why cloud providers try to gain this transparency for them. But anyway, because the Titan chip in many cases is unpatchable, let's remember this vulnerability found in the Bluetooth last year, and Google recalled the Titan security keys because this vulnerability is based on silicon. But silicon patches in many cases is impossible, so it's make very expensive way to patch, basically to change the device to your customers. So, but let's talk about how modern industry standard bootloaders works. We have a small ROM, which is actually pass the control under the loader and second stage loader. And usually root of trust in these chips tied to the ROM, and ROM is unpatchable. So basically, if we have vulnerability inside the ROM, or somebody from GTAC can basically bypass the ROM validation for the loader, so it's done. And in this case, I would say it is a dangerous place, because if this code not formally verified and still written on C, it's kind of difficult to believe it was no issues there, right? And also the complexity for the support, as example, if the device breaks, we need to understand what happens and actually make a recover. So usually this kind of ROM can unlock serial, UART, or GTAC, and it's create additional attack surfaces. So secure boot fix everything, right, in this case, but it is not really true. So think about, we have this stage 0 boot ROM, verifies, loads, and executes stage 1, stage N, and stage N+1. So basically, if any of these layers have their own vulnerability, but we exploit this vulnerability after validation the level, the root of trust basically transfer it to this stage after that. And attacking it, we basically know we have a full control on the boot process, which is create kind of problematic, and modern secure boots is really complex because of that. Silicon bugs stay forever with the customers, and we need to remember that, because basically checkmate vulnerability create a huge issue where we have more new devices affected by this vulnerability. So what happens, this boot ROM issue inside the silicon, and because we have already devices in the field, all these devices is unpatchable. And because of that, it's still, we can read a lot of research based on this issue. Another good example, it's Intel CSME issue from 2018, which is basically initialize page directory, turns on paging, and maps ROM for CSME. It's a small piece of the code, which is immutable and basically unpatchable in case of the issues. What happens, IOMMU DMA protection turn it on too late, and attacker can have opportunity to remap execution pages to arbitrary physical address, as example to spy flash. That's it, right? So, and these devices in the field, it's a lot of devices still unpatched. So basically, we trust a lot to the hardware, and hardware security is hard because we have a lot of devices, a lot of firmwares supported by different vendors, and different vendors has a different threat modeling process, different requirements. Sometimes it doesn't fit together, and it's hard to have the same line of security on each single chip across the system board. I would say it's almost impossible nowadays because it's no single vendor which is develop everything on their own. We trust blindly anything which is signed and came from the trusted source. Basically, it says we have infinite trust to the signed firmware blobs or any other binaries actually came from the trusted resources, right? And how we can guarantee this binary is not being compromised after it's been built, or the build server been compromised, and after that it's been signed with a malicious code and delivered on the website. So it's really hard in this case to create this validation. Okay, let's talk a bit more on open hardware like RISC-V. So basically, RISC-V changed a lot the threat modeling process because it's open silicon. You can look on the specification. In many cases, it is quite transparent. But of course, if the vendor create their own chip and make a lot of custom things across the silicon, it will be not that transparent. But also, we don't have actually a lot of security technologies implemented on RISC-V. It's why many vendors use the RISC-V as a core ISA and kind of a core things from the specification, but create a lot of other layers or extensions with the security on their own. What happens, we have this freedom, right? So it's basically the picture from Sci-Fi website when you can just design your silicon chip based on the third-party fabrics and RTL components. So in this case, designing the chip process will be very, very simple. It's like basically creating a puzzle. You put a lot of components on the pictures, and afterwards you will get your own silicon. But this simplicity creates a huge problem for the threat modeling and security, because you take third-party component without any understanding how it is secure and fits your requirements on security. And you use in your own silicon, and maybe this silicon also can be unpatchable with these third-party components, and it will be create additional risk for your customer. So we really need to be less excited and more precise on your security requirements before basically silicon gets released from the factory. Another actually thing which I want to pay your attention, it is the fault injection attacks. Because a lot of small chips doesn't have a good protection from fault injection attacks, like say voltage breaching, electromagnetic fault injections, and many others, or like power side channel analysis. And actually, I really like this tweet from Nick Timmers, where he say, like, fault injection attacks do not scale well, but their results does. And it is actually very true, because, okay, if you create the single fault injection attack and extract the third-party firmware, you will be basically get the firmware for the analysis after, if you find the vulnerability in this firmware, it will be scaled, right? Or you can share this firmware with other researchers, and it's also kind of a scaling for reverse engineering. So also, it can be extracted security keys and other vulnerabilities identified in the firmware, so it's distributable, right? Fault injection attacks are just the first step in many cases to complete a chain of the attacks. And this single point, it's very dangerous actually, and especially with the places where the physical access, it should be inside the threat modeling, like automotive, data centers, and many others. So it's why I would say we need really rethink fault injections from in your threat modeling. And sometimes we should think, if this device is a customer device and everybody can buy from Amazon, so if researchers really want to attack this device, they will be get from Amazon, extract the keys, and distribute over the internet. So it's a different story. And in this case, you need to think more as a researcher or like architect about your threat model and what kind of the circumstances can be created on the fault injection side. So usual chips for the hardware security, it has a fuses, it has some encryption algorithms used. Usually it is symmetric and sometimes asymmetric, and it is random number generators, and of course in the fuses we have the keys. And sometimes this chips looks pretty simple. And actually this picture I took from Security Dangle. I would not name the company, but they really say we have a top grade security for our dongles and can save your private keys. But this chip was not created and certified for the critical security places. That means we can find a lot of weird stuff about this chip. And basically, this diagram on the right side shows how IS key can be leaked over the power side channel analysis. And also, this particular chip is locking GTAG over set up the pin during the boot. So very interesting chip to be a security used in the security dangle, right? It's why I say we have a lot of different problems across different devices, which is create hardware security, make it secure, hardware security hard. And we need to understand the full picture on your threat model and security requirements. It's not enough. Security requirements, it is just the first step which you think about your level of security. So you create the security requirements, you create the threat model, but after that, offensive security team in your company should go over and understand the reality of your threat modeling. I would say internal pen testing with offensive security researchers on your device created by your company, it is really where the threat modeling meets a reality. Because in many cases, the requirements can miss something. The threat modeling on the early stages, it's very different when we actually understand or get the first silicon. So I would say modern threat modeling process, it's very difficult, and it should be involved many people from the company which is building and working on this project related to the device, whatever, and without this, it's actually make it very hard to make it secure. We really need to rethink the meaning of hardware security and realities of the modern threat landscape, because the threat landscape is changing really fast, but our understanding about the threat model really sometimes it's just freezing for the years, and we try to think about the attacks which is already not very relevant, and we don't have the visibility about new attacks which actually modern attackers can use. It's why offensive security research team, it's very important to gain this visibility and create productive collaboration between the product teams and offensive security research to develop the secure products for your customers. Thank you very much for your attention, and I will be happy to answer all the questions